Hello everyone, welcome to Probability and Statistics for Data Science. When we analyze data, we often compute averages to determine the typical value of quantities of interest. In probabilistic modeling, such quantities are represented as random variables. Because of that, it's very useful to define an averaging operation that can be applied to random variables. And that's what we're going to do in this video. This operation is called the mean. And our goal is to define the mean, which is an averaging operation for random variables. When we have a data set with real values, it's obvious how to compute an average. We just sum up all the data points and divide by the number of data, and that gives us the average. How can we do this for a random variable, which is a variable that is described in terms of probabilities, in the case of discrete random variables, or of probability densities, in the case of continuous random variables? In order to define such an average, we're going to go back to our intuitive definition of probability. So remember that when we first defined probability, what we said is that when we model uncertain phenomena, we imagine that they are experiments that could be repeated over and over and over. So then the probability of an event is the fraction of times the event would occur when we repeat the experiment many, many times. If we have a certain random variable A, remember that we write random variables with this squiggly line on top, the probability that the random variable is equal to a certain constant value, here written without the squiggly line, that indicates that it's just a constant value, intuitively is the fraction of times that this event occurs, the event that the random variable is equal to that value, when we repeat the experiment many times. So basically that corresponds to the fraction of samples or the fraction of data that are equal to that value, where the quantity that is represented by the random variable is equal to that value. We're going to use this intuitive definition of probability to derive a reasonable definition for the average of a random variable. So now let's imagine that we have samples from a discrete random variable that can take values in a certain set A. Here you can imagine that the set A maybe just contains 3 and 4. So we want to express this average of a large number of samples in terms of the probabilities associated to the random variables. In order to do that, we're going to reformulate this sum, and we're going to say that this sum essentially can be written in the following way. We take every possible value that the random variable can take, and we multiply it by the number of times we see it in the data. So here we would take, for example, 3, and then multiply it by the number of times that 3 appears in this sum. Then we would take 4, and we multiply it by the number of times that 4 appears in this sum, and so on and so forth. So hopefully you see that the sum on the left is going to be equal to the sum on the right. Why have we reformulated the sum in this way? Because now we have this fraction, which is the fraction of data points equal to each of those values. What is that when we divide it by n and we have many, many, many samples? This is the intuitive definition of the probability that the random variable is equal to that value. So this is the probability that the random variable is equal to that value when we have many, 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 many samples. What is that probability? It's just the PMF of the random variable evaluated at that value. So now we have transformed the average in terms of samples into a weighted sum of all the possible values of the random variable weighted by the corresponding probabilities. This is exactly what we wanted. We wanted a formula for the average of the random variable that only depends on the probabilities associated to the random variable. And we call that the mean first moment or expected value of a discrete random variable. This is an operator, if you want to get mathematical, that maps a random variable, which is a function mathematically, to a single value. This is why we write it with these square brackets. Okay, this is not too important, but just so you know that's why we've chosen this notation. This sum, which we have defined as the mean of the discrete random variable, may not converge. So it's possible for certain random variables that can take very large values or very negative values with non-negligible probability for this sum to diverge. In that case, without, I'm getting a little bit ahead of ourselves because we haven't even talked of the law of large numbers, but we will see that what happens then is that when you take averages of samples from those random variables, then the average will not converge as it does for normal random variables according to the law of large numbers. But let's not get ahead of ourselves. Just so you know, the sum might not converge. In that case, the mean of the random variable might be infinity, or it might be not well defined. Let's do an example. Let's imagine that we have a random variable that models the goal difference in a soccer game. So here, the probability that we have -2 goal difference is 0.1. The probability that we have goal difference of +1 is 0.25, and so on and so forth. How do we compute the typical number of goals, the expected value or mean of the number of goals? We apply our formula. So what are we going to do? We're going to sum all the possible values of the goal difference and multiply them by their corresponding probabilities and sum it up all together. So we have -2 times 0.1, -1 times 0.2, and so on and so forth. When we sum it all together, we get that the mean of the goal difference is 0.2 goals. As simple as that. Now let's imagine that instead of being interested in a certain quantity, we're interested in a deterministic function of that quantity, for example, the square of that quantity. How can we compute the average of a function of the quantity in terms of the probabilities associated to the corresponding random variable? If we just consider the data points, just some samples from that quantity, this is very easy to do. We just apply the function, here we're calling this function h, we apply the deterministic function to each of the data points, and then we compute the average normally. We compute, for example, the squares, and then we average. That gives us an average of the function applied to the data. How can we transform this into an expression that only depends on the probabilities associated to the random variable that represents that quantity? We do exactly the same thing as before. What we say is that this sum at the end of the day can be expressed as the sum over every possible value of the random variable that these samples can take. We take h of a, h of the value, instead of the value itself, because we're summing the function applied to the data points. And now here we have to weight each of these possible values, like h3, for example, by the number of times that 3 appears in the data. h4 we weighted by the number of times that 4 appears in the data, and so on and so forth. And again, we have an expression where we have this fraction of the data equal to each of these values. That is just equal to the probability. When we have many, many samples, intuitively it equals the probability that the random variable is equal to those values. So now we have an expression for the mean of a function of a random variable, again in terms of the probability mass function, which gives us the probability that the random variable is equal to each of its possible values. And this is how we define the mean of a function of a random variable. Again, it is possible for this sum to not converge. In that case, that function of the random variable would not have a well-defined mean, or the mean might be infinite. Let's take a look at an example. In our goal difference example, we might be interested in the number of points gained by the team that we're interested in from that game. In case you're not familiar with soccer, in soccer leagues, usually when you lose, goal difference is negative, you get 0 points. If you tie, you get 1 point, and if you win, you get 3 points. So now the question is, what is the mean or the average number of points that is going to be gained by this team? We could derive the PMF of the number of points, and in fact, we have done this previously in another video. But what if we're only interested in the mean? Then we don't need to rederive the PMF of the number of points. We can directly apply our formula. So we want the mean of the number of points. That's a function of the goals. What we're going to do is we're going to take that function, we're going to apply it to every possible value of the goals, and we're going to weight it by the corresponding probability of the goals. So here, I recommend actually that you stop the video and do it yourself just to see if you have the idea right. What we're going to do is we're going to take, for example, -2, apply the function is equal to 0, and then multiply times the probability that the goals are equal to -2. -1 the function is also 0. Again, multiply by the probability. For 0, the function is equal to 1. And we're going to again multiply by 0.3, which is the probability, and so on and so forth. We obtain that the mean number of points gained by the team is 1.5. And again, we don't have to derive the PMF of the points in order to be able to compute this mean. Right now, let's take a look at what happens when we have a function of several discrete quantities. So here we have a data set that corresponds to pairs of values, and we're going to interpret them as samples from the joint distribution of a random variable A and a random variable B, each of which have their own discrete range. And we're interested in a certain function of the data, maybe the sum x plus y, or some other function. And we want the average of that function. So again, just from the data points, it's very easy to do this. We just apply the function to each pair, we sum them all up, and we divide by the number of pairs. We're done here. But what we want is an expression in terms of the probabilities associated to these random variables. In order to do that, we recast this sum as the sum of the function applied to every possible pair of values. So we go over the range of A and the range of B here, and we consider every possible pair of values, and then we see how many times that particular pair of values appears in the data set. So hopefully you see that this sum over here and this sum over here are going to be the same. For example, the pair 3, 4, we multiply h of 3, 4 times the number of times that we see 3, 4 in the data set, and so on and so forth. We do this for all the possible pairs. And of course, we divide by n on both sides. So now, why have we done this? For exactly the same reason as before. Now we have this fraction, which is the number of pairs of samples for which the first random variable is equal to a certain value and the second random variable is equal to another value at the same time. That's just the probability of the intersection between the events that maybe I'll write this out. This is just the probability that the first random variable is equal to this value and the second random variable is equal to this value at the same time. That is given by the joint PMF of the two random variables evaluated at this pair of values. So now we have an expression for the average that we're interested in terms of the joint PMF of the two random variables. And that's how we define the mean or expected value of a function of two random variables. Again, if the sum converges. We can apply exactly the same reasoning to the random variables, whatever number of random variables, or to the entries of a random vector. So here we have a d-dimensional random vector. We have a certain function that goes from d values to a single one. The mean of that function can be obtained by summing over the range. So here the range of each of the entries of the random vector is denoted by this set x. So the range of, just to be clear, the range of the ith entry is denoted by xi. So we sum over all of the possible values and we apply the deterministic function to every possible sequence of d values and multiply by the corresponding probability, which is given by the joint PMF evaluated at that sequence of values. If the sum converges, this gives us the mean of that function, that deterministic function of the random vector. Let's do an example with two random variables. Here we have the joint PMF of the number of cats and dogs that are in households in a certain city, and we're interested in the mean of the sum. So what are we going to do? We're going to consider all the possible combinations. So the cats go from 0 to 3 and the dogs go from 0 to 2. So that's why these sums go from 0 to 3, 0 to 2. We're going to apply the function to every possible pair of values, and we're going to multiply by the corresponding probability of those pairs. So again, I recommend that you pause the video and do it by yourself, but let's get to it. So we have, for example, the pair So here we have 0, 0 we can ignore because we're going to multiply 0 times the probability. That's gone. Then we have 1 plus 0 equal to 1 times 0.15. 0 plus 2 equals 2 times the corresponding probability, 0.1. Maybe a more interesting one. For example, this one, we have 2 dogs and 1 cat, so that's going to be 3. It's this guy. And we multiply by the corresponding probability. So hopefully you see how that works. In the end, we get that the mean number of animals in each household is 1.05. All right, so we have seen how we can define averages of discrete random variables or functions of discrete random variables or discrete random vectors. What if we have continuous quantities? So now consider a data set that has these real values that can be interpreted as samples from a continuous random variable A. In order to compute the average, we can do exactly the same thing. We just sum up all the values and divide by the number of data. That's still a reasonable way to obtain a typical value, even if the data points are real valued. What do we do? How do we derive an average of the continuous random variable that approximates this average when we have many samples? Now things get a little bit complicated. We're going to define a grid that on the real line where the grid values are separated by epsilon. I'll draw a picture in a moment. And we're going to try to express the sum of many samples from the continuous random variable in terms of the values on that grid. So let me show you the expression. We're going to say that we have the real line, okay? And we're going to have a grid of the real line where the grid separation is epsilon. So this would be, for example, A minus 1, A0, A1, A2. Okay, this covers the entire real line. And the data points, maybe I'll draw them in green. The data points happen to be here. Okay, so there's data points in different places on the real line. Now what we say is that the sum of the green points can be expressed in the following way, approximately, if epsilon is very small. We're going to take the values on the grid. Maybe I'll use another color to highlight this. So we're going to take the values on the grid, okay, these guys, and we're going to multiply them by the number of data points that are close to them. So here we would multiply A minus 1 by 1 and A1 by 3. So you see that if epsilon is very small, this sum is going to approximate the sum of the data points because each data point is going to be assigned to a grid point that is very close to it. All right. So now we have an expression in terms of this grid. This expression includes a fraction that is very useful to us. It's the fraction of data points that end up between AM minus epsilon and AM. When we have many samples, by our intuitive definition of probability, that's the probability that the random variable ends up between AM minus epsilon and AM. And now, since we have a continuous random variable, we're going to try to express this probability in terms of the probability density of the continuous random variable. Remember that the probability density of a random variable is the probability that the random variable is in a certain interval divided by the length of the interval. So this probability can be expressed in terms of the density at AM multiplied by the length of that interval, again, when epsilon is very small. So now we have an expression for the average, which is in terms of the density of the random variable multiplied by this small number epsilon, and we're summing over a grid over the whole real line. So you remember your calculus, when we take the limit of this when epsilon goes to 0, what we get is a Riemann integral, which is equal to the integral of this function. Here this differential is what epsilon becomes, multiplied but we have an integral of this whole function. What is this function? It's A times the density at A. Okay, again, the convergence of this sum to an integral is just by basic calculus. And this is great because now we have exactly what we wanted. We have an expression for the average of these data points in terms of an integral, well, in terms of an expression that only concerns the probability density of the random variable, which is how we describe and manipulate the continuous random variable. This is how we define the mean, first moment, or expected value of a continuous random variable, if the integral converges. If the integral does not converge, the mean of the random variable can be either infinite or not well defined. Let's do an example. Imagine that we have a uniform random variable in AB. What happens if we have many samples from the uniform random variable and we take an average? What should that equal to? Well, that typical value is the mean, well, will approximate the mean of the random variable. What is the mean equal to? According to our formula, we're going to take all the possible values of the random variable and weight them by the density and then take the integral. So here, the density is only known 0 between A and B, and it's equal to 1 over B minus A because the density has to integrate to 1. When we take this integral, this is just the antiderivative of this guy is just u squared divided by 2. From A to B, we have b squared minus a squared divided by 2 times b minus a. You should actually just, again, pause the video and do this yourself. I should have said this at the beginning. Remember that this guy is equal to b plus a, sorry for my handwriting, times b minus a. So the b minus a is cancelled out and we get a plus b divided by 2. This makes a lot of sense because this happens to be the midpoint of the density, the uniform density of the random variable. Okay, so what if we have a function of the continuous random variable? We can repeat exactly the same reasoning with the grid points and so on, but now replacing the values by the function of those values. And what we will get is that a reasonable definition for the mean of a function of a random variable is the function weighted by the density and integrated over the whole real line, again, if the integral converges. Let's do an example. We had talked about current and voltage for a certain circuit when we were discussing functions of random variables. So here we have a current C in a certain circuit with a certain PDF, and the power over a certain resistor with resistance R is equal to W, the random variable W, which is a function of the current. It's the square of the current times R. So we define this in this video on functions of random variables. When the current looks like this, it's uniform between -1 and 1. The power actually looks pretty weird. Okay, it has this expression. It looks like that. So what if we don't want to? What if we are only interested in the mean of the power? And we don't want to have to derive this PDF. Remember that the way you derive it is you compute the CDF in terms of C, and then you differentiate and so on. Imagine that we don't want to do any of that. We can actually compute the mean directly. How do we do that? We apply our formula. What's the mean of the power? We integrate the mean of the power is the mean of this deterministic function of the current. So now we're going to integrate that deterministic function times the density, which is 1 over 2 between -1 and 1, because it has to integrate to 1. The antiderivative of c squared is c cubed divided by 3. So this integral is equal to r over 3. We have been able to compute the mean of the function without having to derive the PDF of the function of the random variable. If you have a function of several continuous random variables, you do the same thing. You apply the function and now you multiply by the joint PDF. So here we would have an argument with a grid for one of the variables and a grid for the other variable. And we would basically talk about when you are in different squares of this grid. It's essentially the same idea. Also similar to how we defined the argument that we had for 2 discrete random variables. So this is the mean of a function of 2 continuous random variables if the integral converges. Similarly, if we have a continuous random vector with d entries, we take the function that we're interested in, we weight it by the density of the random vector at the different points, and we integrate over the d entries. If the integral converges, that's the mean of the function of the random vector. Let's do an example. Imagine that we grab an amount of sugar uniformly from like a jar or something, and that amount of sugar is between 0 and 1 kilograms. We have pretty big hands. And then we spill an amount that is uniformly distributed between 0 and whatever quantity we grabbed. What is the mean amount of sugar that we have spilled, the expected amount of sugar that we have spilled? We're going to apply our formula to compute this. So what's the distribution of the sugar that we grab? It's uniform between 0 and 1 kilograms. What is the distribution of the sugar that we spill? It's uniform between 0 and whatever amount we grabbed. So this gives us the conditional PDF of the sugar that we spilled S, given the sugar that we grabbed G. So these are going to allow us to characterize the joint distribution of S and G. So now what is the mean of S? We're going to interpret S as a function of S and G, which it is. The reason we do that is because we don't have the marginal distribution of S, we only have it in terms of G. Of course, we could derive that marginal PDF and just compute the mean, but we're going to see that it's actually easier to just interpret S as a function of S and G. So if we do that, if we interpret S as a certain function of S and G, which of course it is, we can apply our formula where the mean of that function is equal to the function weighted by the joint PDF and then integrated with respect to the two variables. So when we do that, we're going to express the joint PDF as the marginal of G because we know it's uniform, and the conditional, because we know that, again, it's uniform conditioned on G. The first one is the amount of sugar we grabbed is uniform between 0 and 1, so we multiply by 1 the PDF here. And then we have the conditional PDF, which is equal to 1 over G from 0 to G. Okay? Again, I really recommend that you try to do this on your own also. We now integrate first with respect to S, right? So the antiderivative of S is S squared over 2. So this is going to be G squared over 2 divided by G is going to be G divided by 2. Now, when we integrate this from 0 to 1, the antiderivative of G is G squared divided by 2. We get that the mean amount of sugar that we spill is equal to 1/4. And our formula allows us to do this without having to derive the distribution of S. All right, what if we have discrete and continuous quantities? We could do essentially the same argument that we did for discrete quantities and continuous quantities. The continuous quantity here, we would have to have a grid and get epsilon to go to 0, but the argument would be very similar. At the end of the day, if we have a function of a continuous and a discrete random variable and we want the mean, what we do is we weight it by the marginal of the continuous, the marginal density of the continuous random variable times the conditional PMF of the discrete random variable, or vice versa, because remember that we have the chain rule for discrete and continuous random variables, so this is going to be equivalent. And then we sum over the discrete random variable and integrate over the continuous random variables. If this sum and integrals converge, then the mean of that function is going to be equal to the result. Let's take a look at an example. Remember that we talked about coin flips when we talked about Bayesian models. Imagine that we flip a coin, but we don't know the probability of heads, and we want to take a Bayesian viewpoint where we have a prior on it, and our prior is going to be uniform in 0, 1. Now, what is the mean of the coin flip? If we are not interested in anything else other than the mean, we can actually compute this directly from the marginal and the conditional without having to derive the probability mass function of the coin flip. So we're going to represent the coin flip by A. We're going to sum over the possible values of the discrete random variable. Now, what is this function of the two random variables of which we're computing the mean? It's just A. Okay, so we're interpreting, just to be clear, we're interpreting A as a function of theta, and A. All right, it's a pretty simple function, but it's still a function. And this will allow us to compute this mean without having to derive the PMF of A first. All right, so once we have that, what is the density of the parameter theta? It's 1, right, because it's uniform from 0 to 1. Now, what is the conditional probability of A given theta? For 1, it's equal to theta. For 0, it's equal to 1 minus theta. So the 0 goes away because we're multiplying by the value of A. So we just have theta integrated from 0 to 1. The antiderivative is theta squared, so we have 1 over 2. I realize, by the way, that I go from theta to theta. I think in the UK, you should say theta, and in the US, you should say theta. But I'm from Spain, so I just do it randomly. Sorry about that. Okay, so we have now defined an averaging operator, that operation that we can apply to discrete random variables, continuous random variables, discrete and continuous random variables, and so on. How do we estimate this when we have data? If we are not interested in the whole distribution of a quantity, we just want its average, well, we just compute the average. It's as simple as that, right? So we call this average, if we want to be fancy in like in statistics, we call this the sample mean, but all it is, it's the arithmetic average. So you get all your data points, you sum them up, and you divide by n. This is the same for discrete and continuous quantities, which should not surprise you, because we started from an average for both the definition of the mean for discrete random variables and also the definition of the mean for continuous random variables. So this should come as no surprise. We're going to see this later on, but if you had really independent, identically distributed samples from a certain distribution that has finite variance, when you consider this quantity, it is going to converge to the mean of the random variable when you have a lot of samples. Often in probability books, this is shown as, oh, look, so interesting, so surprising. They start by defining the mean without really giving much motivation. And then at some point they're like, oh, you can approximate the mean in this way. Oh, look, it converges. Well, of course it converges because, as we saw at the beginning of the video, we have defined the mean of a discrete and of a continuous random variable so that they essentially have to equal the average under reasonable assumptions. So this should come as no surprise. In fact, that's the main motivation for defining the mean mathematically as we have done it. It's so that at the end of the day, it approximates these averages that you would compute from data. So why is computing averages useful when you have a real data set? Well, because it allows you to summarize data very efficiently. So imagine that we have hourly temperatures from 134 weather stations in the US. Looking at 134 PMFs would get, very tiring. But instead, we can just plot the means at each weather station. Here I've made the radius of these markers proportional to the mean temperature, and we immediately see where it's warm and where it's cold. So this is the United States, this is Hawaii. We see that in the south it's warm, and in the north it's very cold. Okay, and near the coasts it's not as cold, especially the west coast. We see also that in Hawaii, in case you're wondering, there's one place which is very cold and one place which is very warm. That's the place that is very cold is on the top of Mauna Loa volcano. It's at such a high altitude that it is cold there. So hopefully you see here that the mean provides a very efficient summary of the data. We have 134 potentially random variables here. We can immediately see the typical values for each of them by just looking at their means. So what have we learned? We have learned a definition of an averaging operation that can be applied to random variables, which we call the mean, and we can apply it to discrete random variables, continuous random variables, and even functions of random variables. And that's all I got. Thank you very much.